Good morning. I am Aditi, studying in BSc Chemistry Honors, first year, second semester. Today we are reading chapter number 5, Chemical Kinetics of Physical Chemistry. So we start introduction. During the study of various reactions which may be carried out in the laboratory or industry or may be occurring in the life process or any other applied field, we are interested to know how fast the reactions occur. The rate of reaction, we are further interested to know how the reaction occurs, the steps in which the reaction occurs, called the mechanism of the reaction. Also, we are interested to know how the rate of reaction is affected by changing the concentration of the reactants or temperature or adding a catalyst, etc. The branch of physical chemistry which deals with the study of the rates of reaction, the factors which govern these rates and the mechanism by which the reactions proceed is called chemical kinetics. Further, a chemist is not interested in the kinetic study of all reactions. For this purpose, the various reactions are divided into three categories. Those reactions which take place almost instantaneously, example many ionic reactions like those reactions which take place extremely slowly, for example, rusting of iron, combination of hydrogen and oxygen at ordinary temperatures, etc., are such reactions which take months or even years before any detectable change occurs. Those reactions which take place at measurable speeds between the two extremes discussed above, there are a large number of reactions which take place at speeds which can be conventionally measured. A few examples included in this category are ethyl acetate to acetic acid or ethyl alcohol, cane sugar, glucose, fructose, ammonium nitrite in the presence of heat, hydrogen peroxide. A chemist is mainly interested in the kinetic study of reactions belonging to these category only. Another question that immediately arises in our minds is why the speeds of different reactions are different. And obvious reason is that a reaction involves the breaking and making of bonds. Since different bonds require different amount of energy for breaking and different amount of energies are involved when different kind of new bonds are formed. The rates of different reactions are different. The instantaneous nature of the ionic reactions is due to that fact that these do not involve any breaking of bonds as ions are already present in the aqueous solutions. Lastly, it may be mentioned that all chemical reactions do not proceed in a simple way. Complications are caused in the study of the rates of reactions when the reaction is reversible or some side reactions take place simultaneously. In the present chapter, we shall take up the different aspects concerning the kinetics of the reactions. Rate of reaction. The rate of reaction may be defined as the speed or the velocity with which the reaction takes place, or the rate of a reaction may be defined as the change in the concentration of any one of the reaction or products per unit time. For example, consider the dissociation of PCl5 to give PCl3 and Cl2. Rate of this reaction equals to decrease in the concentration of PCl5 divided by time taken, or increase in the concentration of PCl3 or Cl2 divided by time taken. Units of rate of reaction. Since the concentration is usually expressed in moles liter and the time is taken in seconds or minutes, the units of the rate of reaction are therefore mole liter inverse second inverse or mole liter inverse minute inverse or atom s inverse, etc. for gaseous reactants and products. However, a difficulty arises in stating the rate of reaction as above. This is because according to the law of mass action, the rate of a reaction depends upon the molar concentration of the reactants, and the concentration of the reactants keep on decreasing with the passage of time while that of the products keep on increasing. Therefore, the rate of reaction does not remain constant throughout. Thus, we should take the rate of a reaction only at a particular instant of time. Hence, the rate of reaction is defined as follows. The rate of a reaction at any time, called instantaneous rate, is defined as the change in the concentration of any of the reactants or products per unit time at that particular time, instant of time. Expressing the rate of a reaction. Since the rate of reaction is changing continuously throughout the course of this reaction, therefore, to state the rate of reaction at any particular instant of time, a small interval of time dt may be taken during which the rate of reaction may be assumed to be almost constant. Suppose dx is the small change in concentration of any of the reactants or products during the small interval of time d. Then the rate of reaction may be expressed as rate of reaction dx divided by dt. Further, if the rate is expressed in terms of one of the reactants, a negative sign is attached to show that the concentration is decreasing. If rate is expressed in terms of any product, a positive sign is used to show that the rate of this reaction may express in any one of the following ways. Rate of reaction, where D, A, dB represents small decrease in the concentration of A and B respectively, and dP and T Q represents small increase in the concentration of P and Q, respectively in the small interval of time dt for a more general reaction of the type. A unique value of the rate of reaction can be contained by expressing the rate of reaction as follows. Rate of reaction is equal to, you can see this. Remember that rate of reaction is always positive. Negative sign shows decrease in the concentration of the reactant, so that is equal to plus a positive sign. Measurement of the rate of reaction. In order to measure the rate of a reaction, the progress of the reaction is followed by studying the concentration of one of the reactants or products at different instants of time. The most common practice to do so is to withdraw small amount of the reaction mixture 2 ml or 5 ml at different instants of time, cool it down immediately to nearly 0 degrees Celsius to arrest the reaction called freezing the reaction, and then find out the concentration of the reactant or the product by suitable method, usually by titration against a suitable reagent. However, this method is not preferred when some of observable property like volume, pressure, optical rotation, etc. changes with time and can be observed directly at different like instants of time without stopping the reaction. It is important to mention that factors like temperature, etc., which affect the rate of this reaction, are kept constant during the kinetic study of the reaction. If concentration of one of the reactant is studied at different instants of time and these values are plotted against the corresponding times, a graph for the type shown in figure 5.1a or b is obtained. You can see this figure graphical method for measurement of the rate of the reaction. The rate of reaction at any time may be studied by either of the following two methods. A tangent may be drawn on the curve at the point corresponding to the time at which the rate is required. The slope of the tangent will then obviously give the rate of reaction at the time, because slope is tan theta is equal to OB divided by OA, delta x delta t is equal to dx divided by dt. Second, the small change in concentration dc corresponding to small interval of time dt may be noted directly from the graph figure 5.1b. Then, assuming that the rate remains constant during this small interval of time, the rate may be calculated as dc divided by dt. If concentration of one of the products is studied at different instants of time and the values are plotted against the corresponding times, a graph of the type shown in figure 5.1c is obtained. The rate of reaction at any time is obtained by finding the slope of the tangent to the curve at the point corresponding to that time as shown in figure 5.1c. Factors influencing the rates of reactions. The rate of reaction depends upon a number of factors. A few important out of these are as follows: name of the reactant, concentration of the reactant, temperature of the system, presence of a catalyst, nature of solvent, presence of radiation. Each of these factors is described below one by one. Nature of the reactant. To understand how the nature of the reactant plays an important role in influencing the rate of a reaction, let us consider the following two examples: oxidation of ferrous ions and oxalate ions by acidified KMnO4 solution. Both reactions are similar as represented below. At the same temperature, say room temperature, the first reaction is very fast, whereas the second reaction is quite slow. as indicated by the rate of disappearance of pink color of KMnO4. In fact, in the titrations, the second reaction is so slow that heating is required. Thus, in the above case, even if the concentration of similar reactants are taken to be same in the two reactions and the temperature is also kept the same, the rates of these reactions are still different. This is obviously only due to difference in the nature of the reducing agents. Fe2 positive ions and C2O2 minus negative ions, oxidation of nitric oxide and carbon monoxide by air. These reactions may be represented as. Thus, the above two equations are exactly identical in the balanced form but still at the same temperature. The first reaction is fast whereas the second is slow. Again, in this case, also clearly the difference in the reaction rates must be due to difference in the properties of NO and CO. As mentioned in section 5.1, the difference in the rates may be attributed to the fact that a reaction involves breaking of the bonds of the reacting molecules and the formation of new bonds in the product molecules. Energy is required for the breaking of bonds and energy is released when a bond is formed. The net energies involved are different for different reactions and hence the rates are different. Concentration of the reactants. As the reaction proceeds, the reactants are consumed. Therefore, the concentration of the reactants decreases with the passage of time. It is observed experimentally that the rate of reaction also decreases as the time passes. This clearly indicates the rate of reaction is directly related to the concentration of the reactants. The variation of the concentration of a reactant and hence that the rate of reaction with, with time may be represented graphically as shown in figure 5.2. That the rate of reaction depends upon the concentration of the reacting species is further confirmed from the simple example of rusting of iron. Rusting of iron is faster in the rainy season when the concentration of water vapor in the air is higher than in the dry weather. The effect of concentration is explained on the basis of collision theory of reaction rates. The rate of a reaction depends upon the number of collisions between the molecules. Higher the concentration, greater is the number of collisions. Temperature of the system. Temperature has a very significant effect on the rate of reaction, so much so that a rise in temperature not only increases the speed of the reaction but in many cases it actually interrogates the reaction. Thus, to study the effect of temperature on the reaction rates, two types of cases are observed: variation of concentration of a reactant or the rate of reaction with time. You can see this graph. For most of the reactions may be exothermic or endothermic, the rate of reaction increases with rise of temperature. As a rough rule, in general, the rate of a reaction becomes nearly double or sometimes even treble for every 10 degree rise 10 degrees Celsius rise of temperature. This is generally expressed in the form of temperature coefficient as temperature coefficient is equal to m, where Kt and Kt plus 10 are the specific reaction rates at T degrees Celsius and T plus 10 degrees Celsius respectively. To cite simple examples, the temperature coefficient for the dissociation of gaseous hydrogen iodide, but for the combination of methyl iodide and sodium ethoxide is solution. The value is about 2.9. It is really a fantastic observation because the number of collisions increases only by about 2% for 10 degree rise at ordinary temperatures, whereas the reaction velocity may increase by 100 or 200% or even more. B. A large number of reactions are known which do not take place at room temperature but occur readily at higher temperature. Example: reaction between hydrogen and oxygen to form water take place only when an electric spark is passed. Similarly, it is well known that coal can be kept in oxygen for years without burning, but once the agitation is ended, it goes on till the whole of the coal burns away. The above observations are explained on the basis of collision theory. According to this theory, substances react because their molecules collide with each other. All collisions are, however, not effective collisions. An effective collision is that collision which results into a chemical reaction. In order that a collision may be effective, the colliding molecules must possess a certain minimum amount of energy called threshold energy. This threshold energy may be defined as the minimum amount of energy which the colliding molecules must passes in order that the collision between them may be an effective collision. The term specific rate has been explained in section 5.6 in brief for a reaction involving the reactants A and B if the rate of reaction is given by. Then we write the constant K is called the specific rate or rate constant. The concept of effecting collision and threshold energy is just like the fact that the some damage occurs to colliding cars only if they have a certain minimum speed. If they collide with a speed less than this speed, no damage may occur to the cars. The two types of cases may now be easily explained as follows. Explanation of the increase in reaction rate with rise to temperature. The different molecules of the reactants do not possess the same energy. If the energies of the reacting molecules are plotted against the corresponding fractions at a particular temperature T, a curve of the time shown in figure 5.3a is obtained called Maxwell's distribution of energies and the figure even represents the threshold energy. The shaded area represents the fraction of molecules with energies equal to or greater than the threshold energy. As the temperature is increased from T to T plus 10 degrees Celsius, the curve shifts as shown in figure 5.3b. The shaded area beyond even now becomes almost double. This shows that the fraction of molecules possessing energy equal to greater than the threshold energy becomes almost double, hence the rate of the reaction also becomes almost double. You can see the figure 5.3 distribution of energies of the reactants. Explanation of the known occurrence of reaction at room temperature and occurrence at higher temperature. At room temperature, there are no molecules possessing energy greater than the threshold energy, and so there is no reaction. When temperature is increased, the molecules of the reactants absorb heat energy, and thus a number of molecules start attaining energy equal to or greater than the threshold energy, and hence the reaction starts. The extra amount of energy which the molecules of the reactants have to observe so that their energy becomes equal to the threshold energy is called the activation energy. In other words, activation energy is equal to threshold energy minus energy actually possessed by the reacting molecules. Thus, in order that the reactants may change over to product, they have to absorb some energy and thus cross a barrier called activation energy barrier. This situation may be represented graphically, shown in figure 5.4. Illustration of the concept of activation energy. The concept of energy barrier may be elaborated as follows. Consider a hypothetical gaseous reaction A2 plus B2 to AB. In order that the collision between the molecules A2 and B2 may be effective, they must first freeze a transitory short-lived intermediate called activated complex. In the formation of this complex, in the bonds in A2 and B2 are loosed and new loose bonds between A and B are formed. Thus, formation of AB molecules may be represented as follows. Thus, the energy barrier corresponds to the formation of an activated complex. Hence, activation energy may be defined as the difference between the energy of the reactants and that of the activated complex. Further, from figure 5.4, it may be seen that even though the energy of the products is lower than that of the reactants and the overall reaction is exothermic, still the system has to claim the energy barrier before it can change over to products with lower energy. Another important result that follows from the above discussion is as follows. Those reactions which otherwise look to be similar but have different rates, even when all other factors are kept the same, can be explained on the basis of the fact that their activation energies are different. The lower the value of the activation energy, the higher will be the rate of reaction. Mathematically, it is observed that the fraction of molecules having energy equal to or greater. Hence, if Z is the collision frequency of binary collisions, the total number of binary collisions per second per liter, number of effective collisions will be hence. Further, it is observed that in a number cases the experimentally observed values of the rates of the reaction are found to be less than those calculated from the above equation. This is because the rate of reaction depends not only upon the energy factor but also upon orientation factor. The colliding molecules must have proper orientations at the time of the collision. Taking this factor into account, we have where P is called the probability or steric factor. Presence of catalyst. A catalyst is a substance which increases the speed of a reaction without itself undergoing any chemical change. For example, the decomposition of KClO3 is greatly accelerated by the addition of a small quantity of MnO2, which itself does not undergo any chemical change during this reaction. The presence of a catalyst provides an alternate path with lower energy barrier as shown in figure 5.5. This activation energy is lowered and hence a greater number of molecules can cross the barrier and change over to products. Further, from figure 5.5, the following two additional results may be derived. For the catalyst reaction is the same as delta E for the uncatalyzed reaction. For reversible reactions, the activation energy for the reverse reaction is lowered to same extent as for the direct reaction. Hence, the presence of the catalyst in such reactions increases the speed of the forward reaction and that of the backward reaction to the same extent. Consequently, the equilibrium is attained equally but it is otherwise not disturbed. Nature of the solvent. In terms of dielectric constant of the solvent, in case of reactions taking place in solution for the given ions at a particular temperature, the rate constant K of that ionic reactions is found to vary with the dielectric constant of the solvent according to the equation, where A and B are constants for the given pair of ions. Thus, a plot of in K versus 1 by D is a straight line. The equation shows that ln K varies inversely with the dielectric constant of the solvent at a given temperature, figure 5.6. In terms of polarity of the solvent, the polarity of the solvent affects the rate of reaction according to the following general rule. A polar solvent is expected to accelerate a process in which a polar substance is a product and retard the process in which the product formed is non-polar. For example, in the reaction between triethylamine and ethyl iodide, the product is a salt and hence more polar than the reactants. The rate of the reaction would increase as the polarity of the solvent increases. On the other hand, in the acylation of alcohol reaction between acetic anhydride and ethyl alcohol, the products are less polar than the reactants. Therefore, the effect of solvent is reverse of that in the first case. In the decomposition of nitrogen pentoxide, the difference in the polarity between the reactants and the products of the rate determining step, possibly nitrogen trioxide and oxygen, is so small that the rate is almost independent of the nature of the solvent. In terms of interaction of the reactants or activated complex with the solvent, it is found that the solvent affects the rate of reaction significantly due to interaction of the reactants or the activated complex with the solvent. The effect of the interaction is to lower the potential energy of the substance by an amount equal to the energy of solvation if one or both the reactants are solvated but the activated complex is not. The decrease in the potential energy of the former means that the required activation energy for the reaction is increased. The rate of reaction will therefore decrease if the activated complex is solvated but the reactants are not. The potential energy of the activated complex will decrease, which means lowering of the required activation energy and hence increase in the rate of reaction. In case the reactants as well as activated complex are solvated, the potential energy of both will decrease, the effect on the overall activated energy and hence the rate of reaction will be small. For this reaction, the reaction between triethylamine and ethyl iodide in nitrobenzene has exponentially high rate. Presence of radiation. Some reactions which do not take place under ordinary conditions take place in the presence of light. Example, the reaction between H2 and Cl2 to form HCl. Such reactions are called photochemical reactions. The reason is that the radiations give energy which is absorbed by the reacting molecules and thus the energy barrier is easily crossed. Order of a reaction and specific reaction rate. In order to understand what we mean by the order of reaction, consider the general equation general reaction. Experimentally, it is observed that the rate of this reaction may not depend upon all the concentration terms of A and all B concentration terms of B. Suppose experimentally the rate of the reaction is found to depend upon concentration terms of A and B, concentration terms of AB. Then we may write where A and B are the molar concentrations of A and B respectively. K is a constant called velocity constant, rare constant. If all the concentrations are taken as unity, hence the rate constant may be defined as the rate of reaction when the concentration of each reactant is taken as unity. That is why the rate constant is called specific reaction rate. Equation 1 is called the rate law. It differs from the law of mass action in the fact that whereas the rate law states that the rate of reaction depends upon the concentration terms on which the rate of reaction actually depends as observed experimentally, the law of mass action is simply based upon the stoichiometry of the equation. For example, in the above case, the sum of the concentration terms on which the rate of reaction actually depends as observed experimentally is called the order of the reaction. Thus in the above case, order of reaction. Hence, the order of a reaction may also be defined as the sum of he exponents to which the concentration terms in the rate law are raised to express the observed rate of reaction. Depending upon whether alpha plus beta is equal to 0, 1, 2 or 3, the reactions are said to be of zero order, first order, second order and third order respectively. Alpha and beta are called the orders of the reaction with respect to A and B respectively. For better understanding, a few examples are given below. N2O3 dissociates as experimentally it is found that it depends only on one concentration term, hence the reaction is said to be of first order. Experimentally, it is found that rate of reaction it depends on one concentration term of NO2 and one concentration term of F2. Hence, the order of reaction is 2. It is a reaction of the second order. Further, it may be mentioned here that the order of a reaction may not be always a whole number. For example, at 450 degrees Celsius, 723 Kelvin, acetaldehyde decomposes as experimentally it is found that units of rate constant for reactions of different orders for a reaction of nth order, you can say this. These units will also be derived from the expressions for rate constants for reactions of different orders discussed in the following sections. Example, a reaction is found to have a rate constant of 1.2 into 10 raised to 3 liter mole inverse second inverse. What is the order of reaction? On the basis of the units given for the rate constant, the rate of reaction will be 2. Numerical problems on calculation of rate of reaction, order and rate constant. You can see the example number 1. Express the rate of the following reaction in terms of different reactants and products. Given, you can see this. Here's example number 2. The following rate data were obtained at 303 Kelvin for the following reaction. You can see this data in this example. Reactions of the zero order. A reaction is said to be of zero order if the rate of the reaction is independent of the concentration of all the reactants. Obviously, for such reactions, the rate of the reaction remains uniform throughout. There are two types of reactions which have been found to be of zero order. These are number 1, photochemical reactions. Photochemical reactions are those reactions which take place in the presence of light photons. Many such reactions have been found to be of zero order. For example, the combination between hydrogen and chlorine in presence of light may be studied by enclosing these gases in a tube and inverting the tube in a trough of water. You can see the figure number 5.8, study of kinetics of photochemical reaction at A at start of the reaction, B after the reaction proceeds. When the reaction takes place between H2 and Cl2, HCl is formed which dissolves into water and the level of water in the tube arises. Thus, through the quantities of H2 and Cl2 decreases, their amounts per unit volume remain the same. The concentrations of H2 and Cl2 remain constant. Heterogeneous reactions. A heterogeneous reactions means a reaction in which the reactants, products, and the catalyst are present in different phases. Some of these reactions have been found to be of zero order. Two well-known examples of these type are the decomposition of hydrogen iodide on the surface of gold and the decomposition of ammonia on the surface of tungsten, molybdenum, or platinum at high temperatures. The gases molecules of the reacting substances get adsorbed on the surface of the catalyst. The surface is thus fully occupied with the molecules of the reactant. Some of these molecules react to form the products, but immediately new molecules take up their position, and thus the concentration of the reacting molecules remain constant on the surface, and hence the rate of reaction remains constant irrespective of the total amount of the gaseous reactants take initially. Expression for the rate constant for a reaction of zero order. For a reaction of zero order, you can see this derivation step by step. This is the graph in figure 5.9, A and B, plot of concentration versus time, plot of rate versus concentration for a zero order reaction. Reactions of the first order. A reaction is said to be of first order if the rate of the reaction depends upon one concentration term only. Thus we may have for the reaction you can see this here the derivation of reaction of the first order, you can see this step by step. Here let us consider the simple case. Suppose we start with the moles per liter of the reactant A. After time t, suppose x moles per liter of it have decomposed reacted. Therefore, the concentration of A after time t moles per liter, then according to law of mass action, rate of reaction, where K is the rate constant or the specific reaction rate for the reaction of the first order. The expression for the rate constant K may be derived as follows. Equation number 1. You can see this written in the form integrating equation number 2 we get, where I is a constant of integration. In the beginning, when t is equal to 0 and x is equal to 0, as no substances has reacted at the start of the reaction, putting these values in equation number 3, and we get that. Substituting these values of I in equation 3, we get equation 6 is sometimes written in another form, which is obtained as follows. If the initial concentration is C0 and the concentration after time t is Ct, then putting A is equal to C0 and A minus x is equal to Ct, equation 6 becomes, you can see, equation number 7. Equation 5 can be written in the form, you can see this equation can be written in the exponential form. Some important characteristics of first order reactions. Any reaction of first order may obey equation 6, 7 or 10. This may be tested in one of the following ways. Number 1, substitution method. Starting with a known concentration A or C0, the concentration of reactant A minus X or Ct at different intervals of time may be noted. For every value of T, the corresponding value of A minus X, Ct may be substituted in equation 6 or 7. If the values of K thus obtained are nearly constant within the experimental error, the reaction of first order. Graphical method, equation number 7 may be written as, you can see this, and here you can see this figure 5.10, plot of log Ct or log A minus X versus T. This is the straight equation of a straight line. Thus, if log Ct or values are plotted against time t, the graph obtained should be a straight line with a negative slope if the reaction is the first order. You can see the figure 5.10. I earlier told you the intercept made on the y-axis would be log C0 and the slope of the line would be. From this, the value of K can be calculated. If the initial concentration is not known with certainty, as it's sometimes the case in some reactions in which the exact moment at which the reaction started is not known, then to test a first order reaction, an equation is obtained in which the initial concentration A is eliminated. This is done as follows. Suppose after time t the concentration is, and after time t2 the concentration is, then according to equation number 11, 12 and 13 may be written as, you can see this. Subtracting equation 14 from equation 15, we get this, where Ct1 and Ct2 are the concentration after time t1 and t2 respectively. that the reaction is of the first order may be tested either by substitution method or by graphical method. ठीक है, versus T2 minus T1 should be a straight line passing through the origin and having slope. You can see this figure 5.11 plot of log CT1 CT2. You can see here versus T2 minus T1. Second, the time taken for any fraction of the reaction to be completed is independent of the initial concentration. For example, let us test the truth of this statement. For half of the reaction is to be completed, equation 5 may be written as, you can see this equation number 17. When half of the reaction is completed, representing the time for half of the reaction to be completed by T2 equation becomes. Thus, A does not appear in this equation so that T12 is independent of a. Similarly, it can be seen that etc. will also be independent of the initial concentration. The time taken for half of the reaction is to be completed. The time in which the concentration of a reactant is reduced to half of its original value is called half-life period of the reaction. The above result can also be used to a test reaction of the first order. The method is called fractional life method. Third, the units of K are independent of the units in which the concentrations are expressed. This is obvious from equation 6 because in this equation K depends upon the ratio of concentration versus and the time t. Thus, so long as both A and A minus x are expressed in the same concentration units, the value of K is not affected. The units of K therefore depend only upon the units of time t. Depending upon whether t is expressed in seconds of minutes or hours, K would be in second inverse or minute inverse or hour inverse respectively. Examples of the reaction of first order. Broadly speaking, the reactions of the first order may be divided into two categories: reactions taking place in the gaseous or vapor phase and the reactions taking place in solution. The examples of the reaction of the first time are very few while those of the second time are very common. For simplicity, the various examples of the reaction of the first order may be further classified into three types as described below. Reactions involving decomposition of a substance. These are the most common examples of the reactions of the first order. The decomposition of a substance may take place in the gaseous or vapor phase or in the solution, the latter being more common. A few examples of this type are being briefly explained below. Decomposition of nitrogen pentoxide. This was the first reaction studied in the homogeneous gas phase in 1921 and found to be of the first order. The compound nitrogen pentoxide is a volatile solid which decomposes in the gaseous state as well as in the form of its solution in an inert solvent like carbon tetrachloride, chloroform, etc. According to the equation, you can see the equation. When the reaction is carried out in the solution, N2O4 and NO2 remain in the solution and the volume of oxygen gas collected is noted at different intervals of time. It is obvious that volume of oxygen gas collected at time t Vt, volume of oxygen gas collected an infinite time, which is done by heating the reaction vessel. Substituting these values in the first order equation, you can see this. The constancy is the value of K proves the reaction to be the first order. Here the example from the following data for the decomposition of N2O5 in carbon tetrachloride solution at 48 degrees Celsius show that the reaction is of first order and calculate the rate constant. Here the solution, you can see this. Since the value of K comes out to be nearly constant, hence give reaction is of the first order, the average value of the rate constant is equal to 0.01984 minute inverse. Here problem for practice, you can see the question. The following data were reported for the decomposition of N2O5 in CCl4 at 30 degrees Celsius. Second reaction is the decomposition of ammonium nitrite. Ammonium nitrite in an aqueous solution at any moderate temperature decomposes according to equation. The volume of nitrogen gas collected is noted at different intervals of time and the result calculated as in the case of decomposition of N2O5. Here the example, the decomposition of an aqueous solution of ammonium nitrite was studied by placing the apparatus in a thermostat mentioned at a particular temperature. The volume of nitrogen gas collected at different intervals of time was as follows. You can see this From the you can see this data. Now from the above data prove that the reaction is of the first order. Solution: if the reaction is of the first order and it must obey the equation, you can see this. In the present case, the volume of K at each instant can be calculated as follows. You can see this data. Since the value of K comes out to be nearly constant, and hence give reaction is of the first order. Here for problem for practice, in an experiment on the decomposition of an aqueous solution of ammonium nitrate at a certain temperature, the volume of nitrogen gas collected at different intervals of time was as follows. Show how the above data illustrate that the reaction is of the first order. Here the reaction number 3, the decomposition of benzene disonium chloride. Benzene disonium chloride, which is known to exist only in the form of its aqueous solution, decomposes readily on heating, giving N2 gas according to be the equation. Benzene disonium chloride converted to chlorobenzene. The progress of the reaction is studied exactly in the same manner as in the above two cases. Example: benzene disonium chloride in aqueous solution decomposes according to the equation. Starting with an initial concentration of 10 gram liter, the volume of N2 gas obtained at 50 degrees Celsius at different intervals of the time was found to be as under. You can see this data. Show the above reaction follows the first order kinetics. What is the value of the rate constant? Solution: if the above reaction follows the first order kinetics, it must obey the equation. In the present case, you can see this data. The value of K at different instants can be calculated as follows. Since the value of K comes out to be nearly constant, the reaction is of the first order. The mean value of K is equal to 0.0674 minute inverse. Here the problem for practice question: benzene disonium chloride in aqueous solution decomposes according to the equation. Kane and Nicole reported the following results of an experiment carried out at 20 degrees Celsius with 35 of a solution containing 10 gram of benzene disonium chloride per liter. You can see this data here. Show that the above reaction is of the first order. Here, reaction number 4, decomposition of hydrogen peroxide. The decomposition of hydrogen peroxide in aqueous solution catalyzed by the presence of finely divided platinum takes place according to the equation. The kinetics of this reaction may be studied either by the same method as done earlier, by collecting the oxygen gas produced and noting its volume at different intervals of time, or by making use of that fact that H2O2 solutions can be titrated against KMnO4 solution, thus by withdrawing equal amounts of the solution usually at regular intervals of time and titrating against the same KMnO4 solution, the amount of H2O2 present can be found every time it is obvious that for the same volume of the reaction solution withdraw. Substituting these values in the first order equation, we get the decomposition of hydrogen peroxide as tested by the equation is found to be of the first order. Here the example from the following data show that the decomposition of hydrogen peroxide is a reaction of the first order. Here is the following data, where T is the time in minutes and X is the volume of standard KMnO4 solution in ml required for titrating the same volume of the same reaction. You can see this. Volume of KMnO4 solution use alpha amount of H2O2 present. Hence, if the given reaction is of the first order, it must obey the equation. Note that the symbol X in the numerical problem is in fact. This value of K each instant can be calculated as follows. Here the given data. This the value of K comes out to be nearly constant. Here, hence it is a reaction of the first order. Here the problems for practice questions from the following data show that the decomposition of H2O2 in aqueous solution in a first order reaction, where N is the number of ml of potassium permanganate required to decompose a definite volume of hydrogen peroxide solution. Following data were obtained in the determination of the rate of decomposition of H2O2 when equal volumes of the decomposition mixtures were titrated against standard KMnO4 solution at regular intervals. show that it is a unimolecular reaction. The catalyst decomposition of H2O2 in aqueous solution is followed by removing equal volume samples at at various time intervals and titrating them with KMnO4 to determine the undercomposed H2O2. The results thus obtained are: reaction number 5, thermal decomposition of azopropane. This is a typical example of homogeneous gases reactions of the first order. The decomposition of azopropane on heating take place according to the equation. Since the reactants as well as the products involved in this reaction are all gaseous, the progress of the reaction is followed by simply noting the pressure of the reaction mixture at different intervals of time. It is obvious that for every molecule of azopropane that decomposes, two gases molecules are produced, one of nitrogen and the second of hexane. Thus, the pressure of the reaction mixture increases with the passage of time. At any instant of time t, the total pressure Pt will be the sum of the partial pressure of azopropane, nitrogen and hexane at the instant. If at this instant of time P is the decrease in the pressure of azopropane, then the increase in the pressure of each of N2 and C6H14 would be P. Thus we have this equations. Substituting these values in equation 2 we get. Substituting this value in equation 3 we get. You can see this. But substituting the value of A and A minus X from equation 1 and 7 in the first order equation, you can get that, where P naught is the initial pressure at 0 time and Pt is the pressure at any instant time of time t. Example: the following data were obtained for the decomposition of azopropane at 270 degrees Celsius into hexane and nitrogen. You can see this data. If a reaction of the first order, it must be obey the equation. In the present case, P naught is equal to 35.15 mm, so that 2 P naught is equal to 70.30 mm. The value of K at different instants can be calculated as follows. You can see this following data. The constancy in the value of K proves that it is a reaction of the first order. Mean value of K is equal to 2.06 into 10 raised to power 3 second inverse. Second, reactions involving isomeric charge from one form to the other. The well-known example of this type is the conversion of N-chloroacetylnalide into P-chloroacetylnalide, which takes place in the acidic medium as follows. You can see this. The study of the kinetics of this reaction is based upon the fact that N-chloroacetylnalide reacts with Kl in presence of the acid to give iodine, whereas P-chloroacetylnalide does not. The reaction takes place as follows. The iodine that thus liberated can be found by titration against a standard hypo solution using starch as indicator. It is obvious that for the same volume of the reaction, solution withdrawn at different times. Here the example: in acidic solution, the N-chloroacetylnalide charges into P-chloroacetylnalide. The former can be estimated volumetrically by withdrawing a definite volume of the reaction mixture, adding Kl and titrating the iodine, liberating against hypo solution. The following results were obtained in a particular experiment. Show that the above data conform to the first order reaction. The values of K instant may be followed as follows in this given data. Since the value of K comes out to be nearly constant, the reaction is of first order. Here the problems for practice: the conversion of N-chloroacetylnalide A and into P-chloroacetylnalide was followed by adding Kl solution and titrating the iodine liberated with standard solution. The Ki reacts with A only. Calculate the first order rate constant. Pseudo-unimolecular reactions. Consider the following acid catalyst reactions: hydrolysis of ethyl acetate. Ethyl acetate converted to acetic acid plus ethyl alcohol. Inversion of cane sugar. Sucrose converted to glucose fructose. Both the above reactions are biomolecular but are found to be of the first order. As experimentally, it is observed that for the first order reaction, rate of reaction, and the second order reaction, rate of reaction, the reason for such a behavior is obvious from the fact that water is present in such a large excess that its concentration remains almost constant during the reaction. Such reactions, which are not only truly of first order but under certain conditions become reactions first order, are called pseudo unimolecular reactions. The kinetics of the above reaction have been studied as follows. In this reaction, acetic acid is one of the products, the amount of which can be found by titration against standard NaOH solution, but being an acid catalyst reaction, the acid present originally as a catalyst also reacts with NaOH solution, hence a little careful throughout reveals that for the same volume of reaction mixture withdrawn at different times. Combining first and second, we find that amount of CH3COOH produced at any instant of time, but amount of CH3COOH produced at any instant of time proportional to amount of CH3COOC2H5 that has reacted. Here you can see equation number 1 and 5. We find that maximum amount of CH3COOH, and here from equation 4 and 6 we have this. Substituting the values of A and A minus X from equation 6 and 7 in the first order equation, we get that. Example, here's the example. 1 ml of ethyl acetate was added to 25 ml of N2HCl. 2 ml of the mixture were withdrawn from time to time during the progress of the hydrolysis of the ester and titrate against standard NaOH solution. The amount of NaOH required for titration at various intervals is given below. The value at infinite time was obtained by completing the hydrolysis on boiling. Show that it is a reaction of the first order and find the average value of the velocity constant. Here the solution of this example, you can see this and solve this. Here the following data. In the presence of K, the volume of K at different instants can be calculated as follows. Since the value of K comes out to be nearly constant, the reaction is of first order. The average value of K is equal to 0.00312 minute inverse. Here's some problem for practice questions. Methyl acetate was subjected to hydrolysis and NHCl at 25 degrees Celsius of the mixture were withdrawn at different intervals and titrated with about N divided by 5 NaOH. The following results were obtained. Where N is equal to volume of alkali used in ml, show that the reaction is of first order. Methyl acetate is hydrolyzed in approx 1 NHCl at 25 degrees Celsius. Aliquots of 5 ml each are removed at intervals and titrated with 0.1852 NaOH. Calculate the first order rate constant from the following experimental data. Inversion of cane sugar, sucrose. The hydrolysis of sucrose in presence of a mineral acid takes place according to the equation. Sucrose, glucose, fructose. An important characteristic of this reaction is that the sucrose is dextrorotatory, whereas the products glucose and fructose are dextrorotatory and levorotatory respectively. Further, the levo-rotation of fructose is more, being 90 than the dextrorotation of glucose being positive 52.5 degrees Celsius, so that the mixture as well as whole in is levorotatory. Thus, on hydrolysis, the dextrorotatory sucrose gradually changes into the levorotatory in mixture. It is for the reaction that the reaction is called inversion of sucrose. The kinetics of the above reaction is studied by noting the angle of rotation at different intervals of time with the help of a polarimeter. Suppose readings of the polarimeter at 0 time, reading of the polarimeter at time, polarimeter at infinity time. You can see the figure 5.12, readings of the polarimeter. It is evident that the reading at 0 time will be positive and it would decrease with the passage of time, pass through 0 and ultimately become negative. A little careful consideration shows that the angle of rotation at any instant of time, angle of rotation at any instant time results from results A and 2 we sorry From results 1 and equation 1 and 2 we have substituting the values of a and a minus x from equations 2 and 3 in the first order we get the result. The applicability of the equation for the inversion of circles was first shown by William Lee 1850. It should be noted that the actual value of K of course depends upon the concentration of H positive ions. Here the example, the inversion of cane sugar was studied in 0.9 NaCl at 25 degrees Celsius. The following polarimetric readings were obtained at different intervals of time. Show that the inversion of cane sugar is a unimolecular reaction here above. The data, given data, here the solution, rotation at any time amount of cane sugar. Here the solution of this example, you can solve this. And here the given data about this example. Here example number 1, at 100 degrees Celsius the half-life period for the thermal decomposition of N2O5 is 4.6 seconds and it's independent of the initial pressure of N2O5. Calculate the specific rate constant and this temperature. Here's the solution. Example number 2, a first order reaction is 40% complete in 50 minutes. Calculate the value of the rate constant. In what time will the reaction be 80% complete? Here the solution. Example number 3, the reaction SO2Cl2 presents K1 SO2 plus Cl2 is a first order reaction with K1 is equal to 2.2 10 raised to power 5 second inverse at 302 degrees Celsius. What percentage of SO2Cl2 will get decomposed in 90 minutes when the reaction is carried out at 302 degrees Celsius? Here the solution. Here some problem for practice questions. You can see this. 5.11 Reactions of the second order. A reaction is said to be of second order if the rate of reaction depends upon two concentration terms. Two types of reactions are possible. Reactants involving only one reactant of the type for which the rate of reaction. Here's reaction involving two different reactants. The constant K in the above equation is called the rate constant for reactions of the second order. The expressions for the rate constant K for either of the above two types of reactions may be carried as follows. For reactions involving one reactant only, the general equation for such reactions is: suppose the initial concentration of A is equal to A moles liter. Decrease in the concentration of A at any instant of time is equal to X moles liter. Concentration of A at the instant of time T is equal to A minus X moles liter. Applying the law of mass action, the rate of reaction will be given by. Where K, as already mentioned in the rate constant for the second order reaction, equation number 1 may be written as integrated this equation we get that where I is the constant of integration in the beginning at time t is equal to 0, x is equal to 0 as no substance has reacted at 0 time. Putting these values in equation 2 we get that. Substituting this value of I in equation 2 we get if the initial concentration is written as C naught and concentration at any instant of time t and Cp, then substituting these values in equation 3 we get that. This is another form of the expression for the rate constant of second order reaction for reactions involving two different reactants. The general equation for such reactions may be written as: if the initial concentration of A and B are same and each is equal to a mole liters, then the method of derivation and the ultimate expressions would be same as in the above case. However, if the initial concentrations of A and B are different, then the expression for the rate constant is derived as follows. Suppose the initial concentration of A is equal to moles liter, the initial concentration of B is equal to B moles liter. Amount of A that reacts in time t is equal to X moles liter, then the amount of B that would react in the same time would also be equal to X moles liter. At any instant of time t, concentration of A is equal to A minus X moles liter, concentration of B is equal to B minus X moles liter. And applying the law of mass action, we get that the rate of reaction dx upon by dt proportional to AB. Whereas before K is the rate constant, equation 6 may be written as: resolving the left hand side into partial fractions, equation 7 may be written as integrating this equation we get that where I is the constant of integration. Here the complete derivation of this second order reaction. Note, an interesting result follows from equation 10 if one of the reactant is present in excess AB is axis B will be very large in comparison to A, so that A minus B is equal to minus B and B minus XB. The equation 10 becomes. Fraction of the second order must obey any one of the equations out of 4, 5, 10, and tested either by substitution method or by graphical method. In the former method, values of a and b and x are substituted for the corresponding time t, and the constant c is the reaction to be second order. In the later method, graphical method, if equation may be rewritten as the equation of a straight line, hence a plot of 1 by divided by ct versus t should be if the reaction of second order shown in given figure 5.3, the slope of the line will directly give the equation. The slope of the given equation in figure 5.13 and 5.14. Figure completed, if time taken for half of the reaction to be completed is represented by, then when x is equal to a by 2, t is equal to t half, putting these values in equation 4, we get that. Similarly, it can be seen that for any fraction of the reaction to be completed, the time taken proportional to 1 divided by a. The units of the rate constant k depends not only upon the units of time but also upon the units in which the concentration are expressed. This is obvious from the equation 4, 5, 10 or 11 because there is one extra concentration term in the denominator in which of these equations. For example, using equation 4, the dimensions of k may be calculated as follows. The same result follows directly from equation 5. Thus, if concentration is expressed in mole liter and time in minutes, the units of K will be moles liter inverse, minute inverse, liter mole inverse, minute inverse. If the set times is in second, the units of K will be moles liter inverse, second inverse, liter moles inverse, second inverse. Examples of the reactions of the second order. Reactions taking place in the gaseous phase. Homogeneous gaseous reactions of the second order are very common. In this category are included mostly the thermal dissociation reactions like the thermal dissociation of acetaldehyde, ozone, nitrogen dioxide, chlorine monoxide. Reaction taking place in solution. A few examples of this category includes saponification of esters, reactions of alkyl halides with tertiary amines, conversion of ammonium cyanide into urea. As an example of the gaseous reactions, the thermal decomposition of acetaldehyde, and as an example of the reaction in solution, saponification of esters may be discussed as follows. Thermal decomposition of acetaldehyde. The thermal decomposition of acetaldehyde vapor take place according to the equation. From this equation, the reaction appears to be of the first order, but experimentally it is found to be of second order, and hence it is preferably written as the reactants and the products are all gases. The progress of the reaction is followed by simply noting the pressure of the reaction mixture at different intervals of time. Further, as one molecule of acetaldehyde on decomposition produces two molecules, one of methane and the other of CO. The pressure increases as the reaction progresses. It is obvious that. Here's a derivation, you can see this. Here the example, the thermal decomposition of acetaldehyde was studied by Haynes, Wood and Huschen at 518 degrees Celsius, starting with an initial pressure of 363 mm of Hg. The following results were obtained at different intervals of time. Here the solution of this example. Here are some problem practice questions. Saponification of esters. The reaction of esters with sodium dihydroxide solution is called saponification of ester. For example, the reaction of ethyl acetate with sodium hydroxide solution take place as follows. Unlike the hydrolysis of ethyl acetate, which take place in presence of an acid as already discussed under pseudo-unimolecular reactions, here neither of the reactant is required to be present in accents. Hence, it is found to be a reaction of the second order. The reaction involves NaOH as one of the reactants, the concentration of which decreases as the reaction progresses. Starting with a known concentration of ethyl acetate and sodium hydroxide preferably equal concentrations, the concentration of NaOH at any instant of time can be found by withdrawing a definite amount of the reaction mixture and titrating against a standard acid. It is obvious that for the same volume of the reaction mixture withdrawn at different intervals of time, volume of the standard acid and here the examples, starting with equal concentration of ethyl acetate and sodium hydroxide, the saponification of ethyl acetate was carried out some Volume of the reaction mixture was withdrawn at different intervals of time and titrated with the same acid. The following data were obtained. Here the solution of this example. Example number 2. 100 cc of ethyl acetate and 100 cc of NaOH, each of 0.05 molar concentration, were mixed and placed in a thermostat. 20 cc portions of the reaction mixture were removed after every 3 minutes and added into separate flasks, each containing 20 cc of 0.05 mHCl. The excess acid in each case was found by back titration with 0.05 m NaOH solution. The following results were obtained. Here the solution, and here another practice problem question. There are 3 problem practice question. You can solve this. Here another example. Decomposition of a gas is of second order. It takes 40 minutes for 40% of a gas to be decomposed when its initial concentration is 4 into 10 ki power 2 moles liter. Calculate the specific reaction rate. Here's the solution of this example. Example number 2. A second order reaction in which the initial concentration of both the reactants are same is 25% complete in 600 seconds. How long will it take for the reaction to go to 75% completion? Here the solution of this example. Here another problem for practice questions. You can see this. There are 7 problem practice questions. You can solve this. 5.14 Reactions of the third order. A reaction is said to be of third order if the rate of reaction depends upon 3 concentration terms. The following 3 types of reactions as possible. Reaction involving 3 molecules of different substances A plus B plus C products. Reactions involving 2 molecules of one substance and 1 molecule of another substance. Reaction involving all the 3 molecules of the same substances. The simplest case is the reaction of the last time. The expression for the rate constant of such reaction may be derived as follows. Suppose A is the initial concentration of A and X is the decrease in the concentration of A in time. Then the concentration of A after time t is equal to A minus X. Now according to the law of mass action, the rate of the above reaction at the instant of time t will be given by, where K is the constant for the third order reaction. Here the complete derivation of reaction of third order. 5.15 Some important characteristics of third order reactions. Any third order reaction of time 3A products or of the types A plus B plus C products and 2A plus B products if the initial concentration of A is equal to B is equal to C or A or C naught moles later must obey equation 4th and 5th. This may be tested by the substitution method or by graphically method as usual. The time taken for any fraction of the reaction to be completed is inversely proportional to the square of the initial concentration. For example, the time taken for half of the reaction to be completed, half-life period, may be calculated as follows. Putting these values in equation 4 we get. Similarly, it can be seen that for any fraction of the reaction to be completed, the units of the rate constant K depends upon the units of time and that of the concentration. This may be seen by calculating the dimensions of K with the help of equation 4 as follows. The same result follows directly from equation 5. Thus, if concentration is expressed in moles liter and times in minutes, the units of K will be moles liter minute inverse, and if time is expressed in seconds, that units of K will be moles liter inverse. Second, examples of the reactions of the third order. Reactions taking place in the gaseous phase. Only 5 homogeneous only 5 homogeneous gas reactions of the third order are known so far. Each of these molecules involves nitric oxide as one of the reactants, and the second reactant being either chlorine, bromine, oxygen, hydrogen or deuterium. The reactions may be represented as follows. The reactions taking place in solution. Very few examples of the reactions of the third order taking place in solution are known. Even the order of some of these reactions is doubtful. As an example, let us consider the reduction of ferric chloride by stannous chloride. The kinetics of this reaction is studied by mixing aqueous solution containing equivalent amounts of FeCl3 and SnCl2 and then withdrawing definite amount of the reaction mixture at regular intervals of time, running it into mercuric chloride solution to remove the excess of SnCl2 and titrating the solution against standard potassium dichromate solution to find the amount of ferrous ions present. The reactions reported to be one of the third order earlier is found to be of the second order according to recent investigations. Reactions of higher order of their being rare. Reactions of higher order cause of their being rare. It is observed that whereas the reactions of first order are large in number, the reactions of second order are less in number, the reactions of third order are still less, and the reactions of the fourth or higher order are very rare. The reason for such an observation may be explained on the basis of collision theory. According to this theory, in order to that a reaction may take place between certain molecules, these molecules must come together simultaneously to collide with each other. As the probability or the ethane for three molecules to come together simultaneously and collide are less than those for two molecules, therefore the reactions of third order are fewer than those of second order. Similarly, the chances for the four or more molecules to come together simultaneously and collide are still less. Hence, the reactions of fourth or higher order are very rare. Half-life period. It has already been stated in the preceding sections that the time taken for half of the reaction to be completed, the time in which the concentration of a reactant is reduced to half of its original value, is called half-life period of reaction. The collisions drawn about the half-life period T half for the reactions of the different order as discussed earlier may be summarized as follows. For reaction of zero order, half-life period is directly proportional to the initial concentration. For reactions of the first order, half-life period is independent of the initial concentration. For reactions of the second order, half-life period is inversely proportional to the initial concentration. For the reactions of the third order, half-life period is inversely proportional to the square of the initial concentration in general for a reaction of the nth order. Molecularity of a reaction. According to the collision theory, in order that a reaction may take place, the molecules must come close together and collide with each other. The number of atoms or molecules, ions that must collide with each other simultaneously so as to result into a chemical reaction is called the molecularity of the reaction. In case of simple reactions, also called elementary reactions, the molecularity is simple to some of the molecules of different reactants as represented by the balanced chemical equation. A few examples are given by decomposition of F2O2, dissociation of HI, reaction between NO and O2. The balance equation is. Hence, the molecularity is 3 and the reaction is called thermolecular. In case of complex reactions, reactions involving a number of atoms, ions, or molecules of reactants in the balanced equation usually more than 3. The chances for all the atoms, ions, or molecules of the reactants to come together and collide are very rare. Hence, in such cases, the reactions are supposed to take place in a number of steps. The slowest step is the rate determining step. The number of ions or atoms, molecules taking part in slowest step, the rate determining step is called the molecularity of the reason. Thus, it is obvious that the molecularity of a reaction must always be a whole number, whereas the order of a reaction can be fractional also, as already mentioned. However, in most of the reactions, the molecularity of the reaction is found to be same as the order. Hence, the two are used without any distinction. The examples discussed in the next section will make this point more clear. Mechanism of a reaction. And mentioned above, in case of complex reactions, reactions involving a large number of molecules of the reactants according to the balance equations, the chances for all the molecules to come together and collide are very rare. Hence, in such cases, the reactions are supposed to take place in a number of steps. A series of steps reactions proposed to account for overall reaction is called mechanism of the reaction. The writing of step reactions is usually based upon experimental evidence, the detection of the presence of some short-lived intermediates, etc. However, a complete certainty of the steps is very rarely possible, but one thing is certain: slowest step, called the rate determining steps, must involve the molecules on which the rate of reaction actually depends upon, as observed experimentally and written in the rate law equation. The following examples will illustrate the point more clearly. Mechanism of complex reactions of the first order. Thermal decomposition of nitrogen pentoxide. The above reaction is unimolecular reaction or a reaction of the first order. Second, bromination of propane acetone propanone. The bromination of propanone in dilute aqueous solution is presented by the equation. Equation number third, mechanism of complex reactions of the second order. Combination of NO2 and F2 to form NO2F. Hence, the above reaction is bimolecular reaction or a reaction of second order. Oxidation of hydrogen bromide with oxygen. The oxidation of hydrogen bromide with oxygen in the temperature range 400 to 600 Celsius take place rapidly as follows. Experimentally, it is found that This implies that the slowest step of the mechanism of the above reaction should involve only one molecule of HBr and one molecule of H2. Hence, the probable mechanism is as follows. Oxidation of hydrochloric acid by hydrogen peroxide. The reaction takes place in the aqueous solution as follows. The reaction of the second order and the following mechanism has been suggested. Mechanism of complex reactions of the third order. Oxidation of hydrogen bromide by hydrogen peroxides. Stoichiometrically, the reaction is similar to above the reaction and may be written as. Thus, the reaction is of the third order, keeping in view that the slowest step should involve one molecule of H2, O2 and H positive ion and one Br negative ion. The following mechanism has been suggested for the above reaction. Reduction of nitric oxide with hydrogen, the reaction is. This suggests that the reaction of the third order and the rate determining slow step, should involve two molecules of NO and one molecule of H2. Thus, the following mechanism has been proposed. Distinction between order and molecularity of a reaction. The main points of difference between the order and the molecularity of a reaction may be summarized as follows. Order of reaction, molecularity of reaction. It is the sum of the concentration terms on which the rate of reaction actually depends, or it is the sum of the exponents of the concentration in the rate law equation. In simple reaction, it is equal to the number of molecules of the reactant as represented in the balance equation. In complex reaction, it is number of molecules involved in the slow step. It need to be a whole number. It can be a fractional as well as zero. It is always a whole number. It can be determined experimentally only and cannot be calculated. It can be calculated by simply adding the molecules of the slowest step. It is for the overall reaction and no separate steps are returned to obtain it. The overall molecularity of a complex reaction has no significance. It is only the slowest step whose molecularity has significance for overall reaction. Even the order of a simple reaction may not be equal to the number of molecules of the reactant as seen from the balance equations. For simple reactions, the molecularity can usually be obtained from the stoichiometry of the equation. Methods for the determination of the order of a equation. The methods commonly employed for the determination of the order of a reaction are briefly described below. By using integrated Reer equation. In this method, the initial concentration of the reactant and the concentration of any one of the reactant or product at different instants of time are determined experimentally. Then either of the following two methods can be employed. Substitution method. The appropriate values of A and X are substituted into the integrated forms of the rate equations for the first order, second order and third order one by one. The rate equation, which gives the constant value of K, determines the order of the reaction. Graphical method. As already derived, the integrated expressions for the rate constant for reactions of different orders are. Hence, if plot of concentration Ct against time is a straight line, the reaction is of zero order. If the plot of log A minus x or log Ct against time is a straight line, the reaction is of the first order. If the plot of A divided by A minus x or 1 divided by Ct against time is a straight line, the reaction is of the second order. D. If the plot of 1 divided by A minus x square or 1 divided by C square t against time is a straight line, the reaction is of third order. You can see figure 5.5 graphical method for the determination of order of reaction. It may be noted that both the above methods are hit and trial methods but still are very commonly employed. Numerical problems on the above method. And here the solutions and some problem for practice questions. Since the value of K comes out be fairly constant using the first order rate equation, but therefore the reaction is of the first order. By using differential rate equations, this method is based upon the fact that the rate of a reaction of the nth order is proportional to the nth power of the concentration, where K is the rate constant for the reaction and C is the concentration at the instant of time t when the rate is R, hence the two different concentration. Thus, to calculate the values of the order n, we require to know the value of rates R1 and R2 at two different concentrations C1 and C2 respectively. They may be found by either of the following two methods. The change in concentration in an applicable interval of time may be measured. The value may then be assumed to be equal to dc divided by dt at the mean value of C is the interval considered. Two different intervals may be considered during the course of reaction and the values of dct divided by dt and dc2 divided by dt. As already discussed in section 5.4, the concentration of reactant may be plotted against time and the rate attaining in concentration may be found from the slope of the tangent at the point. Obviously, this is more accurate method than the first. Numerical problems on the above method. Example number 1. For the reaction between gases chlorine and nitric oxide, it is found that doubling the concentration of both reactants increases the rate 8 times, but doubling the chlorine concentration above doubles the rate. What is the order of reaction with respect to nitric oxide and chlorine? Here some problem practice question. Fractional change method, half-life period method. It has already been discussed that the time taken for a definite fraction of the reaction to be completed is directly proportional to the initial concentration for reactions of zero order, independent of the initial concentration for the reactions of the first order. Inversely proportional to the initial concentration for the reaction of the second order, inversely proportional to the square of the initial concentration for the reaction of the third order. In general, we can say that where n is the order of the reaction. The time taken for half of the reaction is to be completed is called half-life period and is represented by T half. Here the numerical problems on the above method. There are two numericals. Here some problem practice questions. Ostwald's isolation method. This method can be used for finding the order of those reactions which involve two or more reactants. The method is based upon the fact that the order of reaction does not depend upon the concentration of those reactants which are taken in excess. Turn by turn, all reactants expect one are taken in excess. The order thus observed is with respect to the reactant that has been isolated from the others. The total of the overall order of the reaction is the sum of the orders found with respect to the different reactants one by isolation. For example, suppose a reaction involves three reactants A, B, and C. In the first case, B and C are taken in excess so that A is isolated. The order thus observed is the order with respect to A. Similarly, by taking A and C in excess, the order with respect to B can be found, and by taking A and B in excess, the order with respect to C can be found. Suppose the orders with respect to A, B, and C are found to be alpha, beta, and gamma respectively, then the overall order of the reaction is alpha, beta plus gamma. Alternatively, keeping the concentration of all the other reactants constant, the concentration of one of the reactant is changed, doubled, trebled, etc. turn by turn, and the effect on the rate of reaction is studied. In this way, the order with respect to each reactant can be found, and hence the overall order of the reaction can be determined. This is illustrated below with the solved example. Here are some solved examples and problems for practice questions. Complications in the determination of the order of a reaction simultaneously reactions. The various rate equations derived and the methods discussed for the determination of the order of a reaction are based upon the assumption that there is no distributing factor to reaction under consideration. However, in actual practice, complications arise quite often because of the following reactions take place at the same time called simultaneous reactions along with the main reason: opposing or reversible reactions, consecutive reactions, parallel or side reactions. We shall now discuss each of these simultaneous reactions one by one. Opposing or reversible reactions. If N is a reaction, the reactants react to form the products, and the products also react to give back the original substances under the same conditions. So it is called a reversible reaction. In other words, the reaction takes place not only in the forward direction but also in the backward direction. The forward reaction is opposed by the reverse reaction. Depending upon the order of the forward reaction and that of the backward reaction, different cases may be considered as follows. Case 1. When both forward and backward reactions are of first order, this is the simplest case and may be represented as follows. If the velocity constant for the backward reaction Kb is very small as compared to that of the forward reaction, the former can be neglected in comparison to the latter. However, if the forward and the backward reactions take place at compressible rates, time rate equation has to be modified as follows. Suppose A is the initial concentration and A and X is the decrease in the concentration of A in time t. Here's the derivation of this reaction. Here are some solved examples. Case number 3, when a second order reaction is opposed by a first order reaction. And here example, consecutive reactions. It has already been discussed that in the case of complex reactions, the order of the reaction is usually not equal to the molecularity of the reaction as observed from the stoichiometry of the equation. Such reactions are therefore supposed to take place in a number of steps. The slowest step is the rate determining step. The various step reactions thus written for the overall reaction are called Consecutive reactions. For example, let us consider the general equation reaction. Suppose by experiment the rate of reaction depends upon one molecule of A and one molecule of B. The slow step should therefore involve only one molecule of A and one molecule of B. The step reactions or the consecutive reactions may therefore be written as. Each one of these step reactions has its own velocity constant. Suppose it is K1 for the slow step and K2 for the fast step. K1, K2, the overall rate of reaction depends upon the first step only and is not affected by the first step. However, if the values of K1 and K2 are comparable in magnitude, the rate of the overall reaction depends upon both the constants and the situation becomes complicated, making the order even fractional in some cases for the thermal decomposition of acetaldehyde at 450 degrees Celsius, which take place as. To discuss the result of consecutive reactions mathematically, let us take the simplest case when the consecutive processes are both of first order with A reacts to form B as one of the products which further reacts to form the final product C, and K1 and K2 are the rate constants for the first and the second step respectively. Suppose the initial concentration of A is equal to C naught. After time t, suppose the concentration of A and B and C are Ca, Cb and Cc then. The expressions for the variation of Ca, Cb and Cc with time can be obtained as follows. Expression for Ca, you can see this, and expression for Cb, you can also see this derivation. Here the expression for Cc. Keeping in view the expression for Ca, Cb and Cc derived above, their variation with time may be represented as shown figure 5.16. Variation of concentration of A and B, C with time in the flow first order consecutive reaction. Thus, concentration of A decreases exponentially. Concentration of B first increases to a maximum and then decreases, whereas concentration of C increases steadily till it becomes equal to the initial concentration of A. Here the derivation, complete derivation. Example of first order consecutive reaction: radioactivity, decay, decomposition of ethylene oxide, decomposition of dimethyl ether. Parallel or side reactions. If a reaction, the reactants react to form two different products by two different paths such that one product is in larger amount than the other reacting giving the large amount is called main reaction, while the other giving the smaller amount of the product is called side reaction or parallel reaction. If the side reactions take place only to a very small extent, it can be neglected in comparison to the main reaction. However, if two reactions take place in comparable amounts, the rate equation has to be modified as follows. Suppose we start with the moles liter of A and decrease in the concentration of A in time as x moles later. Hence, the concentration of time after T will be A minus x moles later, then assuming that the main reaction as well as side reaction is of first order. The overall rate of the reaction will be, by integration and simplification as usual it gives. From equation 1 and 2, the values of K1 and K2 can be calculated. Parallel or side reactions are very common in organic chemistry. A few examples are given below. Nitration of phenol, chlorination of benzene, reaction of alkyl halides. It may be mentioned here that by adjusting the conditions, the side reaction can be made negligible as compared to the main reaction. For example, in reaction third, if alcoholic KOH is used, ethylene is the main product, and if aqueous KOH solution is used, ethyl alcohol is the main product. Surface reactions. Gaseous reactions which take place exclusively on the walls of the container, which act as surface or on the surface of a solid catalyst, are called surface reactions. The rate of these reactions are affected in a number of ways as derived below. Two assumptions in the study of kinetics of the surface reactions are that the rate determining step of a surface reaction is the reaction of the adsorbed molecules with the surface of the catalyst. Two, rate of reaction is proportional to the fraction theta of the surface covered by the reactant molecules. To understand the kinetics of the surface reactions, we consider here the simplest case involving only one gaseous reactant decomposing on the surface of a solid catalyst according to the reaction. Here case number 1, when the reactant gas is slightly adsorbed, in this case P is very small so that Bp can be neglected in comparison to 1. So we have where K is equal to Kb is the rate constant for the reaction. Thus in the case rate is directly proportional in pressure. Here the derivation. Example of such a case in the decomposition of stibine on antimony it satisfies equation 8 with n is equal to 0.6. Thus, the general expression for the reaction involving only one gaseous reactant decomposing on the surface of a solid catalyst may be written as, you can see this, where n lines between 0 and 1. Retardation by reacting reaction products. In some reactions, the catalytic surface adsorbs not only the reactant but also the product of the reaction. In fact, the product may be adsorbed even more strongly than the reactant. As a result, some surface of the catalyst is covered by the product molecules and hence is not available for the adsorption of the reactant molecules. Consequently, the fraction of the surface covered by the reactant molecules decreases, and so would be the rate of reaction. Hence, the effect of the product being adsorbed on the surface is to retard the reaction. Consider the general reaction. Suppose A is weakly adsorbed and B is strongly adsorbed. Suppose theta B represents the fraction of the surface covered by molecules of B at a time when pressure of A is PA and that of B is PB. Then fraction of surface not covered by B. This is the surface available to A for adsorption, therefore the rate at which A will decompose on the surface will be given by. You can see this derivation. The rate is directly proportional to the pressure of the reactant and inversely to the pressure of the product responsible for retardation. For example, in the decomposition of NH3 on platinum, N2 has no effect on the rate of reaction, but H2 form shows a strong retardation when the product responsible for retardation is moderately adsorbed rather than strongly adsorbed. Here the chain reactions. It has already been discussed that complex reactions take place in a number of steps, and the slowest step it is the rate determining step. However, there are many reactions which take place through the following steps. Chain initiating step. This is the slowest step in which the reactive species, atoms or free radicals are produced. Chain propagative step. The reactive species produced in the first step react immediately with the other molecules of the reactants, producing new reactive species and products. The new reactive species, on combination with other molecules, regenerate the original reactive species. In this way, the reaction goes on. Chain terminating step. Towards the end, the reactive species left behind combine with each other and the reaction stops. The steps second and third are fast because they involve reaction species. A reaction proceeding in a series of successive steps initiated by a suitable primary process is called a chain reaction. Examples: combination between hydrogen and bromine to form hydrogen bromide. Chain initiating step. In the presence of light, bromine molecules dissociate to form the highly reactive bromine atoms. Chain propagating step. The above reaction is immediately followed by the following reactions. Chain terminating step. The left of atoms and then combine with each other or with the molecule of the product and the reaction stops. This is an example of a reaction which proceeds through the free radical mechanism. The measured order of the reaction is 1.5 and the possible mechanism is as follows. Chain initiating step, chain propagating step. Chain terminating step, chlorination of methane. This is another well-known example of free radical reaction. The reaction does not take place in the dark but can be initiated by heating or by the action of ultraviolet light. Once started, the reaction proceeds rapidly. The reaction is considered to take place as follows. Chain initiating step, chain propagating step, chain terminating step. Kinetic study of the chain reactions. The kinetic study of the chain reaction is based upon the principles of steady state. It is assumed that in a chain reaction, the intermediates such as atoms and free radicals, when have low concentrations, acquire constant concentration during the course of the reaction. Two common examples are explained below. Here are the common examples. Unlike the reaction H2 plus I2, it is found that this reaction does not follow simple second order kinetics. 2. It is the experiment data. Rate of radioactive integration. The rate of radioactive disintegration depends only upon the nature of the radioactive element and is independent of the external conditions such as temperature, pressure, etc. Further, it is observed that the radioactive disintegration follows first order kinetics and hence the expression for the rate constant called the disintegration constant can be derived in a similar manner as follows. Suppose a radioactive element A disintegrates to form an element. Suppose n naught is the number of the atoms of the radioactive element taken initially and n is the number of atoms present at only instant of time. Then the rate of disintegration at the instant of time will be given, where K star is a constant characteristic of the nature of the radioactive element and is called decay or disintegration constant. Hence, the disintegration constant may be defined as the fraction of the total number of atoms which disintegrate in 1 second at any instant of time. Here is the derivation. Here examples: after 24 hours, only 0.125 g out of the initial quantity of 1 gram of radioisotope remains behind. What is its half-life period? Second example, the half-life period of is 60 days. What percent of the original radioactivity would be present after 180 days? Here are the examples. Here's some problem for practice questions. Experimental methods of measuring rates of reactions. To study the chemical kinetics of any reaction, the most important measurement is the rate of reaction at different times in terms of any property of one of the reactants or products or of the mixture as a whole, which changes with time at constant temperature based on the property measured at different times. The various methods may be divided into different types as follows: concentration change method, titration method. As the reaction proceeds, the concentration of the reactants keep on decreasing while those of the products keep on increasing. In a number of reactions, it is convenient to measure the concentration of any reactant or product at different times by titration against a suitable reagent. For this purpose, a definite amount of the reaction mixture is pipetted out and then added into ice in the titration flask to freeze the reaction, so that further reaction stops in the titration flask at that particular time as noted from the stopwatch. If the reading for the infinite time when the reaction is complete is required, and it is obtained by heating the reaction mixture. Here are the examples. Pressure change method. This method is used for the gaseous reactions which are accompanied by a change in the number of moles, and hence the pressure of the reaction mixture changes as the reaction proceeds and can be recorded directly on the manometer. Conductometer method. There are some reactions which are accompanied by change in the amount of ions as the reaction proceeds. As the electrical conductivity increases with increase in the amount of ions, therefore the progress of the reaction can be studied by measuring the electrical conductivity. Example of such a case in the decomposition of stibine on antimony. It satisfies equation 8 with n is equal to 0.6. Thus, the general expression for the reaction involving only one gaseous reactant decomposing on the surface of a solid catalyst may be written as, you can see this, where n lies between 0 and 1. Retardation by reaction products. In some reactions, the catalytic surface absorbs not only the reactant but also the product of the reaction. In fact, the product may be adsorbed even more strongly than the reactant. As a result, some surface of the catalyst is covered by the product molecules and hence is not available for the adsorption of the reactant molecules. Consequently, the fraction of the surface covered by the reactant molecules decreases, and so would be the rate of reaction. Hence, the effect of the product being adsorbed on the surface is to retard the reaction. Consider the general reaction. Suppose A is weakly adsorbed and B is strongly adsorbed. Suppose theta B represents the fraction of the surface covered by molecules of B at a time when pressure of A is BA and that of B is PB. Then fraction of surface not covered by B. This is the surface available to A for adsorption. Therefore, the rate at which A will decompose on the surface will be given by. You can see this derivation. The rate is directly proportional to the pressure of the reactant and inversely to the pressure of the product responsible for retardation. For example, in the decomposition of NH3 on platinum, N2 has no effect on the rate of reaction, but H2 form shows a strong retardation when the product responsible for retardation is moderately adsorbed rather than strongly adsorbed. Here the chain reactions. It has already been discussed that complex reactions take place in a number of steps, and the slowest step it is the rate determining step. However, there are many reactions which take place through the following steps. Chain initiating step. This is the slowest step in which the reactive species, atoms or free radicals are produced. Chain propagative step. The reactive species produced in the first step react immediately with the other molecules of the reactants, producing new reactive species and products. The new reactive species, on combination with other molecules, regenerate the original reactive species. In this way, the reaction goes on. Chain terminating step. Towards the end, the reactive species left behind combine with each other and the reaction stops. The steps second and third are fast because they involve reaction species. A reaction proceeding in a series of successive steps initiated by a suitable primary process is called a chain reaction. Examples: combination between hydrogen and bromine to form hydrogen bromide. Chain initiating step. In the presence of light, bromine molecules dissociate to form the highly reactive bromine atoms. Chain propagating step. The above reaction is immediately followed by the following reactions. Chain terminating step. The left of atoms and then combine with each other or with the molecule of the product and the reaction stops. This is an example of a reaction which proceeds through the free radical mechanism. The measured order of the reaction is 1.5 and the possible mechanism is as follows. Chain initiating step, chain propagating step. Chain terminating step, chlorination of methane. This is another well-known example of free radical reaction. The reaction does not take place in the dark but can be initiated by heating or by the action of ultraviolet light. Once started, the reaction proceeds rapidly. The reaction is considered to take place as follows. Chain initiating step, chain propagating step, chain terminating step. Kinetic study of the chain reactions. The kinetic study of the chain reaction is based upon the principles of steady state. It is assumed that in a chain reaction, the intermediates such as atoms and free radicals, when have low concentrations, acquire constant concentration during the course of the reaction. Two common examples are explained below. Here are the common examples. Unlike the reaction H2 plus I2, it is found that this reaction does not follow simple second order kinetics. 2. It is the experiment data. Rate of radioactive integration. The rate of radioactive disintegration depends only upon the nature of the radioactive element and is independent of the external conditions such as temperature, pressure, etc. Further, it is observed that the radioactive disintegration follows first order kinetics and hence the expression for the rate constant called the disintegration constant can be derived in a similar manner as follows. Suppose a radioactive element A disintegrates to form an element. Suppose n naught is the number of the atoms of the radioactive element taken initially and n is the number of atoms present at only instant of time. Then the rate of disintegration at the instant of time will be given. Where K star is a constant characteristic of the nature of the radioactive element and is called decay or disintegration constant. Hence, the disintegration constant may be defined as the fraction of the total number of atoms which disintegrate in 1 second at any instant of time. Here is the derivation. Here examples: after 24 hours, only 0.125 g out of the initial quantity of 1 gram of radioisotope remains behind. What is its half-life period? Second example, the half-life period of is 60 days. What percent of the original radioactivity would be present after 180 days? Here are the examples. Here's some problem for practice questions. Experimental methods of measuring rates of reactions. To study the chemical kinetics of any reaction, the most important measurement is the rate of reaction at different times in terms of any property of one of the reactants or products or of the mixture as a whole, which changes with time at constant temperature. Based on the property measured at different times, The various methods may be divided into different types as follows: concentration change method, titration method. As the reaction proceeds, the concentration of the reactants keep on decreasing while those of the products keep on increasing. In a number of reactions, it is convenient to measure the concentration of any reactant or product at different times by titration against a suitable reagent. For this purpose, a definite amount of the reaction mixture is pipetted out and then added into ice in the titration flask to freeze the reaction, so that further reaction stops in the titration flask at that particular time as noted from the stopwatch. If the reading for the infinite time when the reaction is complete is required, and it is obtained by heating the reaction mixture. Here are the examples. Pressure change method. This method is used for the gaseous reactions which are accompanied by a change in the number of moles, and hence the pressure of the reaction mixture changes as the reaction proceeds and can be recorded directly on the manometer. Conductometer method. There are some reactions which are accompanied by change in the amount of ions as the reaction proceeds. As the electrical conductivity Conductometric method. There are some reactions which are accompanied by change in the amount of ions as the reaction proceeds. As the electrical conductivity increases with increase in the amount of ions, therefore the progress of the reaction can be studied by measuring the electrical conductivity at different intervals of time. Examples: potentiometric method, pH change method. This method is used for the study of the kinetics of those reactions whose pH changes as the reaction proceeds. Potentiometer is an instrument used for measuring the EMF of a cell, which is in turn is related to the pH. Is one of the electrodes is reversible with respect to H positive ion, and the other is a reference electrode, say a calomel electrode. The instrument can then be used for measuring the pH of the solution and is called pH meter. If the electrode reversible with the respect to H positive is the hydrogen electrode, then by applying Nernst equation we get that. Here are the examples. Conductometric method. There are some reactions which are accompanied by change in the amount of ions as the reaction proceeds. As the electrical conductivity increases with increase in the amount of ions, therefore the progress of the reaction can be studied by measuring the electrical conductivity at different intervals of time. Examples: potentiometric method, pH change method. This method is used for the study of the kinetics of those reactions whose pH changes as the reaction proceeds. Potentiometer is an instrument used for measuring the EMF of a cell, which is in turn is related to the pH. Is one of the electrodes is reversible with respect to H positive ion, and the other is a reference electrode, say a calomel electrode. The instrument can then be used for measuring the pH of the solution and is called pH meter. If the electrode reversible with the respect to H positive is the hydrogen electrode, then by applying Nernst equation we get that. Optical methods. These methods include polarimetry, measurement of optical activity; spectrophotometry, measurement of absorption of light; refractometry, measurement of refractive index. The basic principle of all these methods is that the values of these properties depends upon the concentrations. As the concentrations of the reactants and products change during the reaction, the value of the property changes. The first two methods are briefly described below. Polarimetry. This method is used when some reactant or product or both are optically active substances, so that as the reaction proceeds, their concentrations change, and so does their optically actions. Angle of rotation the instrument used is called a polarimeter. Basic principle of a polarimeter in figure 5.17. Spectrophotometry. This method is used upon the principle that the intensity of the radiation absorbed by a substance in a solution varies directly with the concentration of the aim is to find the intensity of transmitted radiation after passing through the reaction mixture at different instants of time during the reaction. The instrument used in spectrophotometer. The basic principles of spectrophotometer is shown in figure 5.18. Effect of temperature on the rate of a reaction, यानी कि Arrhenius equation. The effect of temperature on the rate of a reaction has already been discussed qualitatively in section 5.5, and the various terms involved like threshold energy, activation energy, energy barrier, activated complex, etc. have also been discussed therein. Quantitatively, the effect of temperature on the rate of a reaction and hence on the rate constant K was proposed by Arrhenius in 1889. The equation called Arrhenius equation is usually written in the form as given below, where A is constant cold frequency factor because it gives the frequency of collisions of the reacting molecules. E is cold energy of activation, R is a gas constant, and T is absolute temperature. The exponential factor gives the fraction of molecules having energy equal to or greater than activation energy. The energy of activation A is an important quantity as it characteristics of the reaction. Using the above equation, its value can be calculated as follows. Here is the given derivation, you can see this. Thus, knowing the values of the rate constants K. Optical methods. These methods include polarimetry, measurement of optical activity, spectrophotometry, measurement of absorption of light, refractometry, measurement of refractive index. The basic principle of all these methods is that the values of these properties depends upon the concentrations. As the concentrations of the reactants and products change during the reaction, the value of the property changes. The first two methods are briefly described below. Polarimetry. This method is used when some reactant or product or both are optically active substances, so that as the reaction proceeds, their concentrations change and so does their optically actions. Angle of rotation the instrument used is called a polarimeter. Basic principle of a polarimeter in figure 5.17. Spectrophotometry. This method is used upon the principle that the intensity of the radiation absorbed by a substance in a solution varies directly with the concentration of the aim is to find the intensity of transmitted radiation after passing through the reaction mixture at different instants of time during the reaction. The instrument used in spectrophotometer. The basic principles of spectrophotometer is shown in figure 5.18. Effect of temperature on the rate of a reaction, यानी कि Arrhenius equation. The effect of temperature on the rate of a reaction has already been discussed qualitatively in section 5.5, and the various terms involved like threshold energy, activation energy, energy barrier, activated complex, etc. have also been discussed therein. Quantitatively, the effect of temperature on the rate of a reaction and hence on the rate constant K was proposed by Arrhenius in 1889. The equation called Arrhenius equation is usually written in the form as given below, where A is constant cold frequency factor because it gives the frequency of collisions of the reacting molecules. E is cold energy of activation, R is a gas constant, and T is absolute temperature. The exponential factor gives the fraction of molecules having energy equal to or greater than activation energy. The energy of activation A is an important quantity as it characteristics of the reaction. Using the above equation, its value can be calculated as follows. Here is the given derivation, you can see this. Thus, knowing the values of the rate constant, this equation of the form y is equal to mx plus c, the equation of a straight line. Thus, if a plot of log k was 1 divided t is a straight line, the validity of the equation is confirmed. This is actually found to be as shown for a typical plot. Further, from equation 6, obviously we will have slope of the line EA divided by 2.0303 r. Thus, measuring the slope of this line, the value of EA can be calculated. Here the given figure 5.19 are typical of log K. Here are the examples. Here are some problems for practice questions. Theories of reaction rates. The two well-known theories to explain the rates of different reactions are collision theory, transition state theory, or theory of absolute reaction rates. We shall now discuss each of these theories one by one. Number one, collision theory. This theory is based upon the kinetic theory of gases, according to which the molecules of a gas are continuously moving and hence colliding with each other. Since for a collision to take place, at least two molecules must be involved. Therefore, the simple case to consider is that of biomolecular reactions. Hence, in the discussion that follows, we shall first discuss the collision theory for biomolecular reactions and then for unimolecular reactions. A. Collision theory for biomolecular reactions. In a biomolecular reactions, in order that two molecules may react, they should not only collide but the collision must be associated with sufficient energy so that the molecules are activated. The situation is just like the fact that in order that the damage may occur to two cars, they should not only collide but collide with sufficient energy. This means that all collisions are not effective. The number of effective collisions is only a fraction of the total number of collisions. Hence, if Z is the number of biomolecular collisions per centimeter cube per second and F is the fraction of those molecules that are activated, we can write. Applying Maxwell-Boltzmann law of distribution of energies, the fraction of the molecule in a gas possessing energy greater than a particular value A is given by the equation. This is called Boltzmann fraction or Boltzmann's factor. To test the validity of the collision theory, the following two cases may be considered. Case 1. When the biomolecular collisions are between similar molecules, considering the molecules to be rigid and hard spheres with no forces of attraction or repulsion between them, applying kinetic and theory of gases, the number of collisions per unit volume per unit time or per centimeter cube per second is given by, where v is the average velocity of the gas molecules, sigma is the molecular diameter of the molecule A, and Ne is the number of molecules per unit volume of the vessel. Here the complete derivation. Case 2 is when the biomolecular collisions are between dissimilar molecules, and here's the complete derivation. Here's some examples to illustrate the calculation of fraction, rate constant and frequency factor. The experimentally observed value for the rate constant K for the above reaction at 556 Kelvin is found to be 3.5 into 10 raised to power 7. Thus, keeping in view of number approximations involved, the agreement between the theoretically calculated value and the experimentally observed value is fairly good. Modification of the equation of a collision theory, no doubt a good agreement between the calculated value and the observed value of the rate constant is found for a number of biomolecular reactions in the gaseous phase as well as in the solution. There are many reactions for which the calculated value is found to be much higher than the observed value. Hence, equation for the rate constant is modified as, when the P introduced, and the above equation is called probability factor or steric factor. It accounts for the fact that all collisions between the activated molecules may not result into a reaction. Only those collisions between the activated molecules result into reaction which collide with particular orientations. The value of P varies from 1 to 10 raised to power 9, where P is equal to 1. The reaction obeys collision theory. A limitation of the above explanation is that on the basis of kinetic theory, it is possible to account for probability factor as low as 10 raised to power 3 to minus 10 raised to power 4, but not lower than these. Hence, to account for this limitation, another theory has been proposed called transition state theory, as will be discussed shortly. Collision theory for unimolecular reactions, Lindemann hypothesis. A unimolecular reaction in general means a reaction of the type. And such reaction, only one molecule of the reactants take parts in the reaction. Consequently, the question arises, how do molecules in a unimolecular reaction attain their energy of activation? The answer to this question was first suggested by Lindemann in 1922. He pointed out that the behavior of unimolecular reactions can be explained on the basis of biomolecular collisions, provided we suppose that a time lag exists between activation and reaction. During this time, the activated molecules may either react or be deactivated to ordinary molecules. Consequently, the rate of reaction will not be proportional to all the molecules activated but only to those who remain active. This concept may be illustrated as follows. Transition state theory or theory of absolute reaction rates. According to this theory, it is a belief that before the reacting molecules change into products, they form an intermediate called activated complex, which has higher energy than both the reactants and the products as shown in figure 5.4. It is for the reason that they are called transition state theory. The activated complex is in the equilibrium with the reactant molecules, and the rate of reaction is given by the rate of decomposition of the complex to form the products. Thus, we may represent the situation as follows given below. You can see the complete derivation. This equation is known as Eyring equation, as this theory makes use of some fundamental physical properties of the reacting molecules. It is called theory of absolute reaction rates. Significance of the equation of the transition state theory. The equation, it involves two factors. The first factor is constant and constant temperature. Hence, the rate of reaction depends only upon the second factor. This factor involves with a negative sign. This means that at particular temperature, greater is the value of the free energy of activation for a reaction, the slower will be the reaction. Here the comparison with Arrhenius equation, here the complete derivation, you can see this. Advantages over the collision theory. The transition state theory is better than the collision theory in a number of ways. For example, in collision theory, the correction factor P was introduced arbitrarily, whereas in the transition state theory, its inclusion has been justified in terms of entropy of activation. This concept of the formation of an activated complex seems to be more appropriate than assuming that the molecules just collide together and change into products. Here, problems on theories of reaction rates. Some formulas are given, you can see this. Here's some numericals example. You can see this. The activated complex theory, effect of pressure on the reaction rate. The activated complex theory can be applied to study the effect of pressure on the rate of the reaction. Here the complete derivation. You can see this. This equation implies that the rate constant of a chemical reaction increases with increase of pressure. Volume of the activated complex is less than the total number of the reactants.